Right, so welcome to this masterclass from Cambridge Leadership College. My name is Warwick Bailey. I'm one of the Z coaches here. And in this masterclass, we're going to be going through the A-level paper, Planning for A-level Chemistry. And in this paper, it's not particularly testing the knowledge, sort of hard chemical knowledge, but rather testing your ability to conduct laboratory practical experiments. So we should be able to get through this comfortably. It's only 1 hour, 15 minutes. We've got an hour and a half in the masterclass. So we'll go through the questions. You've already seen them, I think, on the seen the responses on the mark scheme. But particularly, we'll try and pull out the comments that the chief examiner makes. And the examiners in their report are just identifying the mistakes that students typically make. So if we try and pull out the comments that the chief examiner makes, then that's strengthening your exam skills to succeed much more with these paper 5 papers. Okay, so the first question here actually should have been familiar, I think, if you've done good GCSE courses, because they start off talking about lithium, cutting it with a knife and putting it into water, and probably that was something that you saw demonstrated during a GCSE course. Possibly not with lithium, more commonly with sodium. You see that in GCSE courses where a teacher will take the sodium out, cut it, and then put the piece of sodium into some water, and then you can see how the sodium reacts with water. So this taking an alkaline metal out and cutting it is something that might be familiar from GCSE demonstrations. And first up, you've got to draw a diagram to show how you do this experiment. You're collecting hydrogen gas as the lithium reacts with water. And particularly, the examiner is asking, let me get the pen working, how the reactants are kept apart until the reaction is started. Now, you can probably remember from GCSE that these alkaline metals react very vigorously with water, and so there's no time to lose. You've got to keep the reactants apart until you mix them, and then the clock starts running. And so there's and your water apart. And I think there's 2 things you could do. And you have to excuse my drawing because you can draw much better than me. But you're going to have like a large tube, and in there, I think you'd have at A-level a gas syringe. I know the mark scheme talked about collecting over water, but a gas syringe is a much more sort of accurate piece of apparatus to be using at A-level. And the stopper gets pushed out, doesn't it, as the hydrogen is generated by the reaction of lithium and water. So you've got a gas syringe there. You can see I'm drawing with pen and without a ruler. When you're in the exam, diagrams are being drawn in pencil, and you're better off using a ruler rather than trying to do it freehand like I'm doing. And one of the comments that the examiners are continually saying to students is you've got to show these kinds of apparatus diagrams where you're collecting gas as being airtight. And the way to typically do that is to show with a hash there that there's a bung in the top of the tube there. Now, the thing is, you've got this thing where you've got to keep the reactants apart until the reaction needs to be started. And the way you can do that is if you have another little tube inside here, you see like that, and that's the water there, and in the tube are the pieces of lithium. Okay, so they're kept apart, and then you can thread like a little piece of cotton down here. And actually, because that bung is so tight and the cotton is so thin, that's still airtight. And what it means is that when you're ready to start the reaction, you can pull the cotton and that'll tip the little test tube that's in there and release the lithium into contact with water. So that's one way of keeping these reactants separate until you're ready for the reaction to start. I think that's one option. Another option, and they referred to this in the Marx scheme, is you could have a flask, conical flask like this, and again you'd have the bung in the top connected to the gas syringe and all the rest of it. So like that. And then you'd have to have some kind of physical separation where you've got the water on one side of a barrier and you've got the pieces of lithium on the other side of the barrier. And all you're going to do is tip the flask slightly so that the water mixes with the lithium. So you've got to choose one of these methods, either the piece of cotton tied to a test tube here so that you can pull the cotton and the lithium goes into the water, or you've got to have this kind of arrangement, which is called, I think, something like a split flask, something like that. So either of those are acceptable. And then when you're labeling this up, again, you're meant to be using straight lines that you're drawing with your pencil and your ruler. And then you write a label on a horizontal line. So even if your line is at an angle like that, you still write your label on the horizontal. And the examiner complained a little bit that some of the diagrams weren't big enough, that students hadn't drawn them clearly enough. I think the rule of thumb here is to get diagrams that are simple but clear. Okay, so you can draw better diagrams with a pencil and a ruler than I can, but having a diagram that shows just enough, no more than enough, simple but clear, sufficiently large, is what the examiner is looking for. Good. Okay, so there's a question here about, you might remember seeing this at GCSE in reactions that your teacher demonstrated with sodium. What you do to take the lithium out to make a sample is you get a pair of tweezers and you pull a lump of lithium out of its containing bottle because it's stored under oil, because it reacts with oxygen in the air. And you pull the lump of lithium out and you place it on a piece of filter paper. And then you can cut a piece of the lithium off that you want. And because it's covered in oil, you should then dry the piece of lithium between two filter papers. And the filter papers absorb the oil, and then the lithium is ready to be used in your experiment. So you've got a couple of points the examiner was asking for here. One is to cut the lithium, because if you remember, it's a soft metal. It's quite easy to cut it with a knife. It's like cutting kind of hard butter. So you're going to cut the lithium with a knife, and then because it's covered in oil, to stop it from reacting with the air, you're going to dry between filter papers. And that just takes the oil off the lithium, ready to be used. Interesting. Next question. And this is the thing, is that in these questions, you have what the examiner calls command words. All right. Now, a command word there is state. And there's another one, which is in here, about observing. Okay. So you've got to state from your observations how you would know the reaction had stopped. Now, some students wrote something like, no, excuse my pen, no more, you can see what I'm trying to say here, no more hydrogen. Now that's true, the reaction stops when no more hydrogen is produced. But the examiner said, even though that's true, you don't get any marks for that because you can't observe hydrogen. It's a colorless gas, you can't see it. So it's not true that that's an observation. So even though it's correct that there's no more hydrogen being created, you had to say the syringe plunger, that's the part that goes into the syringe plunger did not move any further. because that's an observation you can make. You have to, I hope my talking is clear, even though my writing isn't. So the syringe plunger did not move further. Okay, so that's an observation, but the examiner said, well, this one is a deduction, and so that's not true that it's an observation. So this is the thing, is that in these exams, the questions are written very, very carefully, and you have to watch out for these command words so that you answer very accurately and don't say something that feels right, like there's no more hydrogen. You have to give an observation that you could actually make. All right, next one then. 2 precautions. I think that's fairly easy. You could look that up in the mark scheme, and earlier on they gave you some risks associated with lithium. So I think the ones that you saw in the mark scheme there, you can look up pretty easily. Okay, again, I think some easy marks here. Relative atomic mass of lithium is known to be approximately 7. So if the relative atomic mass, symbol for that is Ar, of lithium is approximately 7, then the molar mass is just the same as the relative atomic mass, but with units of grams per mole. All right? And you've got 0.1 grams, that's a mass, and you know your equation that amount, the number of moles, is the mass divided by the molar mass. So if you take 0.1 gram, that's a mass, and you divide it by the molar mass, which is about 7 grams per mole, that gives you the number of moles. And I work that out as 0.01428 moles. You can see I'm not rounding too early because I don't want to lose any precision in the calculation. So I'm not rounding at this point. So I've got that many moles, and I know that 1 mole occupies 24 decimeters cubed. So 0.1428 moles is going to occupy, well, you do that calculation, and you end up with 0.171 decimeters cubed. All right, and you see, the examiner said, well, you know, you could put your answer here, but you must give the answer with a unit, because it says the volume of hydrogen produced, but it doesn't give a unit there. Sometimes they leave a unit there and just expect you to put in the numerical answer. So you're either saying 0.171 decimeters cubed, or it's, I don't know, a little bit more comfortable to say 171 centimeters cubed. Okay, either of those would do. You just know how to convert between decimeters cubed and centimeters cubed. And well, you know, this is a kind of back of the envelope calculation. You're kind of estimating roughly how much gas is going to be produced, how much hydrogen is going to be produced with 0.1 gram of lithium. And the question is then, well, if you know you're going to have 0.171, well, let's do that, 171 centimeters cubed. If you know you've got 171 centimeters cubed through, how big is your gas syringe going to be? Well, it's got to be more than 171, hasn't it? So some students gave the answer of, well, the gas syringe has got to be 172 centimeters cubed. Well, gas syringes don't come in that size, it's too specific. A gas syringe typically comes in a size of 250 centimeters cubed. And that's a good volume for reading accurately 171 centimeters cubed. So you can't come up with some kind of fantasy gas syringe. Those don't exist. 172 centimeter cube gas syringes don't exist. They're going to be sort of regular whole number volumes, typically 250 centimeters cubed. Some students were putting gas syringes of 10 decimeters cubed, which is clearly very unwieldy. Those kind of gas syringes don't exist. 10 decimeters cubed is 10 liters cubed. Think of that as 10 10 litres of milk or some of 10 litres of water. And that would be a huge gas syringe, doesn't exist. You're looking for a gas syringe of 250 centimetres cubed, which comfortably allows you to accurately read 171 centimetres cubed. All right, so they've talked through one method for determining the relative atomic mass of lithium, measuring the volume of hydrogen that's produced. Another method is to react the lithium with water and then do a titration of the lithium hydroxide that's produced. And they give you this method here. All right? And in step one, you've got to measure 100 centimeters cubed of distilled water. Now, that's kind of an awkward volume because most volumetric apparatus is 50 centimeters cubed. Okay? For example, a burette, as you know, fills up to 50 centimeters cubed. Or you can get one of, if I can draw it, this is a bulb pipette. They look like that, and they have a little mark up there where you can measure out exactly a volume. And those bulb pipettes also go up to 50 centimeters cubed. And the reason they don't go any higher is it becomes very, very unwieldy to use something that's got a volume of more than 50 centimeters cubed. So your choice is either the burette or this bulb pipette, and you know those only go up to 50 centimeters cubed. So the examiner is looking for an answer that you have to use one of these pieces of volumetric apparatus twice. So it wasn't sufficient to say, I will use a burette or I will use a bulb pipette. You have to say, I'm going to use this particular piece of volumetric apparatus, either the burette or the pipette, I'm going to use it twice. And that word twice in there, or 2 times, was required for you to get the mark. And this next question is quite similar to the one we had before about observations. You see, you've got to say how you would know that the reaction between lithium and distilled water is complete. Well, you're going to have to say that the lithium would be bubbling, and eventually the piece of lithium gets smaller and smaller and smaller and smaller until it disappears completely. And that's an observation. So you've got to say here the observation you make, that the lithium becomes smaller until it disappears. You can't say until the lithium has finished reacting, because that's almost a deduction. You've got to be saying what you can actually see, because when he says, the examiner says here, well, what do you know? That's something that you know with your senses. It's something that you observe, not something you deduce with your mind. So that's very similar to the one we had before about making observations, not making deductions. Okay, so the reaction's been proceeding in the beaker, the reaction's finished because you made that observation, and now you've got to transfer exactly 250 centimeters cubed. Okay, and when you take a specific volume like that, the technical word for that volume, although they haven't used it here, is that you are removing an aliquot. Okay, just so you know the vocabulary. You're taking an aliquot out, and the size of the aliquot is 25 centimeters cubed exactly. So how would you do that? Well, you've got a choice of 2 types of volumetric apparatus. You've either got the bulb pipette, which looks like that. Okay, I hope you understand what I mean. My drawing's not brilliant. And it has a mark graduation up there. And when the bottom of the meniscus is at that graduation, then that bulb pipette is containing exactly 25 centimeters cubed. So that's one thing you could use. Another thing that you can use is something called a graduated pipette, which doesn't have the bulb in it, but has a scale on it like this. Okay, and they're both volumetric pieces of apparatus. That's the bulb pipette, and this is the graduated pipette. And really, either of those is acceptable to be used. Okay, next one. You're going to be doing a titration, and this reliability is something to do with the repeat measurements. That's a kind of command word to be thinking about repeat measurements. And again, the vocabulary, when you take repeat measurements with a titration, is to say that you're looking for concordant titers. So the titer is the volume that you add from the burette, and a concordant titer is not only one that's repeated, but one that is repeated within 0.10 centimeters cubed. All right, so let's say you measured in your first titration 25.2. Normally, your first titration is off because it's a test. You're not really sure the value you're going to get. You usually overshoot. It's a test. Your second titration might be 25.05. Now, those aren't concordant because they're not within 0.1 centimeters cubed. So you've got to keep going, and the next one might be 24.95. Now, those are concordant because they're within 0.1 centimeters cubed. So at that point, you can say, I've got that titer and that titer, but not that one. My average titer is going to be the mean of those two there. So you've got two concordant titers. Concordant means a repetition, but a repetition where the value between the two repeats is 0.1 centimeters cubed. And that's how you're going to make sure your titration is reliable. And your vocabulary there is you had a number of titers, and you were happy that your result was reliable when those titers were concordant. All right, now this was, these ones here were the ones that the examiner flagged up that the students had the most difficulty with. And that the first one is that the student has cleaned the beaker and then left some water in the beaker. Now the problem with that is if you look up here, the volume of water that should have been added to the beaker was measured accurately. Do you remember? There was 2 lots of 50 centimeters cubed from a burette, or 2 lots of 50 centimeters cubed from this bulb pipette. So it was important at that point that you had a very, very accurate measurement of the volume of water you're adding to the beaker. And if you've accidentally left some water in the beaker, well, it's no longer 100 centimeters cubed, it might be 101 centimeters cubed. So what that means is that when you do your titration, your concentration is too low, isn't it? So you've got your concentration is low. I'm using kind of shorthand here. You'd have to write this. So that C is for concentration. My arrow down is showing that the concentration that you measure in the titration was too low. And then when you do your titration calculations, you're measuring an amount, aren't you? The number of moles. Now, if the concentration is low, well, the amount, the number of moles, is going to be low as well, isn't it? And later on, you're going to be using the expression that the amount, the number of moles, is equal to the mass divided by the molar mass. If I rearrange that equation so that the molar mass is the subject of the equation, then molar mass is equal to mass divided by amount, the number of moles. And from the molar mass, it's the same numerical value as the relative atomic mass. But you can see there, can't you, because I've now got this inverse relationship, if the number of moles is too low, what's going to happen then to our value of molar mass? The molar mass value is going to end up being too high because I've got an inverse relationship there with the number of moles. So, I've just drawn some shorthand here. You'd have to explain your reasoning, but the chain of reasoning is that the concentration measured was too low, so the number of moles of lithium hydroxide was too low, and therefore the number of moles that comes into this expression here means that you end up with a too large value for the molar mass, and so you end up with a too large a value for the relative atomic mass. That's the kind of chain of reasoning that you need. Now, the other thing that happened was that the student left some water from cleaning in the conical flask. And actually, there's a kind of clue here that that may not have any effect, because it says state the effect if any. And because all you're interested in actually is the number of moles in the titration. And so if you've left a little bit of water in there, that doesn't matter too much because it's the same number of moles in a smaller or larger amount of water. And so they, at this point, you're saying that the amount, that's the number of moles, of lithium hydroxide is unaltered. Okay? Because we're working on an amount of lithium hydroxide here, and it doesn't matter if we've got a little bit more water or not, the same number of moles are still there. And so because the amount, that's N, isn't it? The amount of lithium hydroxide is unaltered. When you plug your N into this expression here to calculate your molar mass, which is going to give you your relative atomic mass, the amount has been unaltered, and so therefore the relative atomic mass is unaffected as well. Okay, good. That was question one then. We'll change gear now and start working on question two. And it's very common actually in these paper fives that a lot of experimental technique, particularly this use of volumetric glassware, is tested in the first question. And then when you come into the second question here, well, you've said plenty about your technique and you've said plenty about volumetric glassware. These second questions tend to be about your mathematical skills and graph plotting skills. That's very, very common about the difference between question one and question two. So there's quite a long preamble here. You're working with magnesium. It's reacting with an acid there to give you hydrogen gas. And you've got an expression here which is derived from something called the Arrhenius expression. You can look that up if you want to. But the Arrhenius expression makes a relationship between the activation energy and the rate. Now this expression over here is something to do with the rate because it's looking at the time that's been taken. And over here you've got the activation energy. So this is some kind of rearrangement or some kind of form of an Arrhenius equation. If you want to go and look that up, you can do that. And the thing that you've got to spot here is they're plotting a graph of that against that. And when you have this word here against, that's what that usually means is you're plotting, or the normal way of interpreting that is you're plotting y against x. Okay, so that word against is the typical vocabulary. When you might say I'm plotting this against that, you're plotting something on the y-axis against the x-axis. And so this expression up here looks pretty fierce, but if that term is going on the y-axis and that term is going on the x-axis, and you can see you've got a term here, haven't you, that's multiplying x. I'm just going to call that m for the moment. That's starting to look a lot more friendly because you're familiar, aren't you, with the expression for the equation for a straight line, y equals mx plus c. And once you recognize that that's going to be your y and that's going to be your x, and this is just some kind of value here, a constant, then you can see that this looks like the equation for a straight line and there's no y-intercept. So the y-intercept is actually 0 there. That's why it doesn't appear. So the y-intercept is 0. That's why it's not in there. And so, you know, you've just got to spot that even though that looks difficult to work with, all it is just another way of saying y equals mx. And you know that y equals mx plus c is your standard expression for a straight line. And that should actually, I suppose, be flagging up in your head that when you come to plot the points, then because we've got, we're expecting some kind of straight line, aren't we? Something like that. If you ended up with a curved line, anything like that, then you're going wrong because the expression we're working with relates to y equals mx, the equation for a straight line. Tells you what you're doing, the 4 steps. And it doesn't tell you how you measure the time taken. Typically, you'd have some kind of stopwatch, and you'd be hitting it with your hand when the reaction starts, and hitting it with your hand again when the reaction finishes. So it's some kind of way that you measure time taken. And we'll come back to that a bit later on, but you can see the time measurement may be open to uncertainty because you've got your reaction times between when you start the clock and when you stop the clock. There's a human reaction time coming in there. This experiment is getting carried out at different temperatures, and so you've just got to do a bit of work with your calculator here, plugging in data into this data table. And they've asked you to work in standard form. They've given you some examples of that already, to 3 significant figures. And then these ones here are being given to 2 decimal places. So you've just got to make sure that you can work in scientific notation, standard form, significant figures, decimal places. And the only one I think that was problematic was that when you came to do this one down here, on your calculator, you ended up with, I think, 3.0487. All right. Now, you've just got to make sure then, because you're working with 3 significant figures, if you look at that one there, that's your first significant figure. That's your second significant figure. That's your third significant figure. The significant figure after that is an 8, which means that this 4 is closer to a 5 than it is to a 4. If you understand what I mean. So your 3 significant figures that go in there is 3.05 times 10 to the minus 3, not 3.04, because actually, as significant figures, 3.05 is closer to 3.04878 than if you're at 3.04. So you just have to watch out for those. I suppose another one over here is the value that you end up with here is 0.9. And you actually have to write the 0 in there because it's asked you in the question for 2 decimal places. So, for example, if you did a calculator and you just put 0.9 in there, you'd be losing a mark because you've got to have the additional 0 for the number of decimal places. So just a couple of things there that, they always choose these values so that some of them end in 0. So you might actually truncate that and have 0.9 rather than 0.90, and some figures. So that's always going to happen, and when you come into these data tables that you've got to watch out for that. Okay, so let me see. So this is a bit awkward, isn't it? Because that's the y, isn't it? And that's the x. Yeah? Normally, you might have the y before the x. Anyway, you just have to watch out for that you're plotting those. And I don't know why they started doing this, but in older exams, they didn't give you the scale. But now in the more up-to-date exams, they've started providing the scale on the graph paper. So that saves you the task. And what happens is that you start plotting the points. I'm not going to do them here because it'll take me forever, but the points are actually on one of these graduations. None of the points fall in between the graduations, so that's quite nice. And all the points fall on these graduations as well. So any cross that you've got should not be in a square like that, because that would be in between a graduation, but it's got to be exactly where those graduations meet. I can do it there like that. So that is wrong. Where the graduations meet, it's correct, because in this example, all the points in the scale that they've chosen for you here have an actual cross in terms of the graduations where the point should be. So you should be expecting, I'm just going to sketch these on, you'll have drawn them correctly. You'll have, say, a cross there, and then you'll have another cross there, and then you'll have another cross. These aren't the right points, I'm just putting them on. You have another cross there, that kind of thing. So you end up doing your best fit line oh sorry, you do your plotting there, and then you're going to take your ruler and try and get the best fit line through that. Now your best fit line, I don't have a ruler, so your line does not look like that, by the way. And I'm drawing this in pen. You'd be drawing it in pencil. So the examiner wants things like diagrams and graphs drawn in pencil. And for elsewhere in the exam, you should be using black ink. But for these parts, you're using pencil. And when you do that, you find that most of the points lie on a best fit line, quite close to a best fit line. But there's one point that was out here somewhere, and there's another point that was somewhere out here. Sorry, I should have drawn that as a proper cross. Now, you'll have plotted them accurately. I'm not plotting them accurately. And because these are anomalies, then you're going to ignore them. And the way that you show that you're ignoring them is you draw a circle around them, and that means that you're not including them in the best fit line that you've been trying to draw. That's the way of highlighting anomalies. And just while we're here, I think when you're plotting your points, you do it across, because that's extremely clear what you're doing. It is acceptable to draw a dot if you're plotting a point, but because a dot is much smaller than a cross, for a dot you're meant to draw a circle around it, like that. And then if that point was anomalous, then you'd have to draw another circle around it. So that would be an anomalous dot. Now you can see that's getting really, really messy. So my advice is to draw crosses, and then if they're anomalous, you draw a circle around them. Trying to draw a dot and a circle and an anomalous point ends up being really messy. So even though that's acceptable and you wouldn't lose marks for it, you can see that it's not recommended. Okay, so we've got this line here. You'll have a much better line than me. I'm just kind of sketching it along here. And you've got to say, haven't you, a little bit more about these anomalous points. Now, I'm going to call that one A, because the examiner asked you to label them both with a circle and with a letter. And then you've got to reference A and say a bit about it, and you've got to reference B and say a little bit about it. So if we start with A, it's anomalous. Now, if you see where the graph is going, A is down here, isn't it? A should have been up here somewhere to be on the line. So that's where A should have been, but it ended up down here. Now, that means that if you look back at this y-axis here, you've got a y-axis which is the logarithm of 1 over the time. And if the point is down here when it should have been up here, then the time is too large. Okay, the value of time is too great or too large. Similarly for B over here, well, B is there, isn't it? But B, if the measurement was done accurately, then B would be down there. And that means that the measurement of B, because it's a time, is too small. All right? Now, this is where we come back to using that stop clock that I mentioned earlier. Well, if the time is too large, that means there's some kind of human error in stopping the clock. Maybe you got distracted for a moment and then you didn't realize the reaction finished and then you stopped the clock. So your time was too large for A. And for B, for some reason, you stopped the clock too early. Maybe you were getting kind of trying to overcompensate for the one that you got wrong just now, and you stopped the clock too early. And so what the examiner is looking for in the points here is point A was the time sorry about my writing, was too large. And for B, the time measurement was too small. Okay. So that, and the reason for that is just human error with the stop clock. Okay. So the difficulty that you had there was to translate the fact that this point was off, and it was off by being too large, and this one was off by being too small in terms of the measurement of time that you were making with the clock. Right, next up, and you should have seen this coming a mile off, is that often when you've plotted your graph, you can be certain that the next question will say, hey, you've got a straight line graph, please calculate a gradient. And so the rule of thumb for the gradient is that your gradient should be at least half of the graph paper. So if, for example, you're measuring a gradient there, that's no good because you're not taking up at least half the graph paper. You've got to take up half the graph paper or more for your gradient. And the trick with these gradients is that you choose one point that's easy. Now, you'll have different values than me, but say I'm looking here. Now, for example, reading off 0.9 is easy. So I'm going to go that point there, my gradient, because the value of x I can read off up here. So for me, that would be 3.12, wouldn't it? So that's 3.12 times 10 to the minus 3 as my x, comma, minus 0.90 for my y. So that's a coordinate there. You've got brackets, one value, comma, sorry, that's the x value, comma, the y value. That's the way you represent a coordinate. And what I meant by choosing one point that's easy is you can't go wrong by reading 0.9. If I'd chosen a point up there, then I've got, point there, then I've got a difficult value to read on the y and a difficult value to read on the x. So that's making my work, it's making life harder for me. So choose an easy value. It doesn't matter if it's an x value or a y value, but choose one of them to be easy, and then you're faster because you've only got one difficult value to read. Right, so you've measured one point up there, you measure another point down here. I've used up more than half the graph paper, and I'm going to have that point as x, whatever it is, and comma y, whatever it is. Okay, that's your convention for recording a data point. And then you're going to do you have your coordinates in here. So you're going to have x, comma y, whatever it was, and then your other one, x, comma y. And these are, you're then going to use these, and your gradient, I'm going to call that, well, your gradient is the change in y divided by the change in x. Okay? Now, the examiner picked up that some of the students got these the wrong way around, because you're going to put up there, probably the first thing that you calculate is going to be the change in y, but that's actually the second coordinate here. Do you see what I mean? So the temptation is, because you're calculating a change of y first, you end up using the x value first. And a number of students fell into that trap and ended up, instead of having delta y here, having delta x. So you calculate your change in y, and then you calculate your change in x. And when I did that, I ended up with my change in y was 0.9, and my change in x was 0.32 times 10 to the minus 3. And you should have a negative value in there. Okay. Now that just comes out in the wash if you do the maths carefully, but even if you didn't do the maths carefully, it should have been in your mind, because this is a negative gradient, isn't it? So when you have straight line graphs, that's a positive gradient, and that's a negative gradient. So you should have been expecting a negative value, and if you ended up with a positive value here, alarm bells should have gone off in your head and said, well, something's not quite right, I'm expecting a negative value. And when I got this, I did that little bit of maths on my calculator, and I got minus 2812.5 as my gradient. Check back to the question. Okay, I've got a negative gradient, but the examiner is asking for 3 significant figures here. So, well, what's that to 3 significant figures? Well, I've got my first significant figure, my second significant figure, my third significant figure, and then the closest third significant figure to 2 is just the 1. So for me, my 3 significant figures was minus 2810, that number rounded to 3 significant figures. Okay, and you see there's 2 marks here, aren't there? Well, you're going to get, interesting, you're going to get a mark for that value being in the right range. You're going to get a mark deducted if you don't get the negative value, and you're going to get a mark deducted if you put something like this down rather than getting it rounded to 3 significant figures. All right, now, earlier on, if you remember, go back, we just said that this kind of monster equation here is just another way of saying y equals mx plus c. Now, you've just calculated, haven't you, the gradient, all right? So all you're expected to say at this point is that the gradient that you calculated, you just did that just now, is equal to that term there, which is minus EA over 0.0191. Okay, and because you're wanting to calculate the activation energy, you've just got to rearrange that so that EA is the subject of the equation. So EA is equal to minus the gradient times 0.0191. Okay, now remember your gradient was negative, so a negative times a negative is a positive times a positive, so the value of EA is going to come out to be positive. And again, you should have been preparing for that, because you know from doing your studies of rates, if that's a reaction profile, let me try and draw it a bit bigger. If that's a reaction profile like that, then this value here is the activation energy. It's positive. Not all molecules that collide have successful collisions. Only those molecules that have an energy equal to or greater than the activation energy. Activation energy is always going to be positive. And so, when you come to write your answer down here, where's it gone? The activation energy, mine worked out at plus 53.7 kilojoules per mole. You've probably got something slightly different. There's a prompt there that you need to be thinking about the sign. Now, those 2 negatives multiplied by each other became positive, which gave you the positive sign. And even if you didn't know that, well, you should know, shouldn't you, that when you draw these reaction profiles, the activation energy is always positive. Okay, so that's why the examiner is just flagging that up. But I think you should have been prepared for that, because you knew the activation energy was positive. And if you ended up with a negative value, you need to go back to your calculator or your calculations and figure out why you're getting a negative value, because it should have been a positive value. Okay, next one then. Something to do with reliability. Okay, now this is interesting, because earlier on, if you remember, when we had these, where were they? These, the examiner was asking us about reliable values earlier on. And that time, the reliability was related to repeat measurements, particularly getting concordant measurements, repeat measurements that were within 0.10 centimeter cubed. So we know normally that reliability is related to repeats. But in this experiment, if you look at the data, there are no repeats. Okay, so there's a slightly different understanding of reliability here. Now, in this case, the reliability is, well, if you've got a best fit line and all your values are close to the line or on the line, then that is a reliable set of results. If they're more scattered like that, then the reliability is less. So reliability normally means repeating, but in terms of a straight line graph, where you haven't got repeat measurements, where you've taken a mean, reliability is related to the scatter. So you could say something at this point along the lines that the scatter is low. This is low scatter, this is high scatter. And that scatter is low only because those anomalous points have been removed. Otherwise, the scatter would be quite high. So the scatter is low when the anomalous points are excluded. Okay, so even though you only got 1 mark here, the examiner is looking for 2 points. First, the scatter is low, and secondly, the scatter is low, that's true, only when these anomalous points are excluded, and you have to have both of those to get your mark. Good, all right, now. Okay, so the student had some data at higher temperatures. Well, that was the point in this experiment. You had high and low temperatures, and the student is saying that it's less accurate at higher temperatures than it is at lower temperatures. Now, is that student correct or not? And then you would explain why. Well, the student, that's a command word, by the way. These are 2 command words, and the command word state, the actual definition of that, is that you write something very briefly. Okay, something as a state is you write it in the smallest number of words as possible, because you're going to have to use your time having a longer set of words here. So state, the command word, means a small number of words. So I think you just write there, student is correct. That's about as brief as you can get. Okay, you're doing a state. Okay, the student is correct. Then you've got to explain why. Well, I'll just be doing kind of shorthand here as well. I'm just trying to explain this. Okay, so let's say you've got a stopwatch that's measuring this time, okay? And maybe it's a digital stopwatch, maybe it's got hands on it, maybe let's have it as a digital stopwatch. And that stopwatch might give you a value of 1.1 seconds or 2.4 seconds, something like that, okay? That means that it's called the measurement uncertainty is half that final value there. Okay, so let's say even if I got a measurement of 10.3 seconds, because it only measures to this 10th of a second there, the measurement uncertainty is expressed as 0.05 of a second. Okay, half of the smallest value there, which would be a 10th of a second. Okay, so that's the measurement uncertainty, right? Now, but then let's say you did one experiment at a low temperature, it took 10.3 seconds, And then you did another experiment at a lower temperature, and that took 30.4 seconds. The measurement uncertainty is exactly the same in both times. Okay, so the measurement uncertainty is the same, but the percentage measurement uncertainty, sorry about my writing, I'll say that again, the percentage measurement uncertainty is different because 0.5 as a percent of 10.3 is a bigger percentage than 0.05 as a percentage of 30.4. So the percentage measurement uncertainty is higher at the higher temperatures. So the student is correct because the percentage measurement uncertainty is higher, is increased at the temperature that's higher. Okay, so the student is correct. The measurement is less accurate because the percentage measurement uncertainty increases when the time taken decreases. Now, something else that happens when you put a piece of magnesium in hydrochloric acid, it can sink to the bottom. Sometimes it floats on the surface. Now, what's that how's that going to impact the experiment? Well, that means that only the bottom surface of the magnesium is in contact with the acid. The top surface, because it's floating on the top, is just open to the air, isn't in contact with the acid. So this is going to mean that the surface area is decreased, and you know actually from your GCSE studies, that means the rate of reaction is also going to decrease. Again, you've got your state and explain. So you're saying that the rate of reaction is going to decrease, and you're going to explain that by saying that the surface area has decreased, and that leads to a reduction in the rate of reaction. The examiner picked up on some vocabulary that students were using. Some students said things like the rate of reaction was shorter. Now, if something's longer or shorter, that's a measurement of distance, isn't it? Okay? It's a shorter distance to college or a longer distance to college. And other students were talking about things being slower or faster. And if something's slow or fast, that's a measurement of velocity. Okay? Now, when I talked about this, I said that the rate of reaction was greater or smaller. And so you're using the correct vocabulary to describe these quantities here. So the surface area is smaller, the rate of reaction is less. So you've just got to make sure you're not using this kind of everyday vocabulary because it's not sufficiently precise in terms of scientific vocabulary. Just watch out for the way you describe things because if something's shorter, you're talking about the quantity of distance. And if you're saying something slower, you're talking about the quantity of velocity. You have to be precise on the language that you're using. Right, last one. Repeat the experiment again. You're using, instead of dilute hydrochloric acid, you're using dilute ethanoic acid, same set of temperatures. State in the smallest number of words and give a reason. Okay? So you're going to say there in the smallest number of words that the initial rate is going to increase. And the reason for that, if you look back here, I'm going to scroll right back. Where is it? Lost it. Okay, here you are. Okay, so what's happening is with ethanoic acid, if you remember, that's only partially ionized in water. There's a reversible reaction, isn't there? And actually not all of the ethanoic acid is ionized. And so even though you might have 0.1 mole per decimeter cubed ethanoic acid, it's not 0.1 mole per decimeter cube hydrogen ions. It's a lot less than that. And if the concentration of the hydrogen ions, one of the reactants, is reduced, then the rate of reaction is going to be reduced as well. Again, that's GCSE knowledge. If you reduce the concentration, the rate of reaction is going to be reduced as well. So, scroll. So, did I get that wrong just now? The initial rate is going to be less, isn't it? That's what I mean. I'm using the correct vocabulary. They're not saying slower or shorter or anything like that. So the initial rate is less. That's what you've stated. You're giving a reason for that. The reason is that ethanoic acid is only partially dissociated, and so the hydrogen ion concentration is lower, and when you have a lower concentration of reactants, that leads to a reduced rate of reaction. Okay, good. So we've got through that paper 5. And actually, that paper 5 is very, very common in its structure. Typically, question 1 will look at your use of volumetric apparatus, and question 2 will look at your use of data, plotting graphs, completing data tables, doing calculations, and so on. So very, very typical question 2. And if you've got any further questions on that, then the Z coaches are available on the Slack channel. And of course, they'll be delighted to take any questions that you have about this paper 5. So please use the Slack channel, talk to the Z coaches there. And it just remains for me to say, I wish you every success in your studies of chemistry and look forward to the next masterclass from Cambridge Leadership College.